I'm happy to be here so I can show you all how to free your storage systems from synchronizing with consensus for a majority of their operations without sacrificing consistency. So applications are becoming increasingly reliant on geo-replicated storage. And this is because replicated storage provides fault tolerance for important application data that cannot be lost. By replicating this data across several replicas located in several geographic regions, clients can access their data even when a server fails or a region becomes inaccessible. Application developers also care about linearizable replicated storage. Linearizability makes it easier for developers to write correct code. This is because linearizability provides the abstraction of a single unreplicated machine executing client requests. And this abstraction is intuitive for developers to reason about, so they don't have to be concerned with how data is replicated underneath the hood of the system. And don't just take my word for it. There's an ever-increasing list of real storage systems that provide both fault tolerance and linearizability. etcd, CockroachDB, Spanner, Azure Storage, and Chubby are just some such examples. So the current state-of-the-art techniques for providing both fault tolerance and linearizability fall into two categories. First, consensus protocols enable robust state machine replication, which allows for the implementation of arbitrarily strong synchronization primitives. However, in order to provide this abstraction, these protocols incur a high latency cost, especially in the geo-replicated setting, where inter-replica latency is on the order of tens of milliseconds. On the other hand, shared register protocols implement read-write registers with fault tolerance. While they cannot be used to implement strong synchronization, shared register protocols provide their simple interface with favorable tail latency. And so in the next few slides, I'll go into a bit more detail about how these techniques achieve or fail to achieve these properties. But at a higher level, our work looks to answer the question, how can we unify these techniques into a single system that achieves the strengths of both without suffering from the weaknesses? State machine replication provides a generic interface for clients to request the execution of commands, which are arbitrary deterministic computations on the state of the state machine. Consensus protocols are used to determine a stable order of commands. For example, a stable order is usually materialized in a log, where replicas agree on the log positions of each command. A command is stable once all of its preceding log positions contain commands, and replicas apply all stable commands in the same order. For example, C1, C2, and C3 are executed in order once they become stable. C4, on the other hand, cannot be executed until a command is ordered in the log position that precedes it. And this technique is used in each of the previously mentioned real-world systems. Because any arbitrary deterministic computation can be represented by a state machine, strong synchronization primitives like read, modify, writes can be implemented with consensus. In fact, consensus is necessary for these types of operations. However, the power of consensus comes with a latency cost. For example, some consensus protocols forced commands to be serialized through a single replica, or they delay the ordering of concurrent commands. This cost is especially felt in the tail of the latency distribution, where best case or common case optimizations are unavailable. Linearizable shared register protocols provide reads and writes with low read tail latency by not imposing a stable order on the operations that modify state. In an unstable ordering, there are no predefined log positions. So replicas do not need to wait for all preceding log positions to be filled before executing write operations. This is safe because writes completely define the state of the register, so the current state only depends on the most recent write. To see this, consider the state of a register after 4 writes have been executed. It is whatever value was written by the most recent write, W4. A write W5 that is concurrent with W4 can be ordered between W3 and W4, even though W4 has already been executed. And this is because the final state of the register, including W5, is the same as without it, namely the value written by W4. In some real-world systems, like Cassandra, Dynamo, or React, are built around this concept of a simple read-write interface for storing data. Now, shared registers cannot be used to implement strong synchronization primitives like read, modify, write. And in practice, they enjoy favorable tail latency relative to consensus protocols due to the flexibility provided by unstably ordering writes. A unified interface that provides the strengths of both consensus and shared registers must support strong synchronization as well as read-write access. Shared objects are a common programming abstraction that supports these via read-write and read-modify-write operations. A read-modify-write reads the value of the shared object to obtain its base value. It then performs some computation on this value to produce a new value and writes this back to the object. These 3 steps are done atomically. This interface is used in real systems, including etcd, Redis, and Bigtable. However, these existing systems do not provide this interface with both linearizability and low read tail latency. We rephrase our earlier question of unification, then, to be how can we provide this interface using consensus for read modify writes and shared registers for low read tail latency? Our answer to this question is with a new ordering mechanism that we call consensus after register timestamps, or Carstamps. To maintain the favorable tail latency of shared registers, Carstamps order write operations with an unstable order. Read, modify, write operations are stably ordered with respect to their base. We call this ordering mechanism consensus after registers because read, modify, writes, which require consensus for proper ordering, are ordered with respect to the shared register ordering of writes, and not the other way around. This unified ordering allows 2 writes to be arbitrarily ordered in the unstable order, even if one has already been executed. At the same time, the stable ordering of read modify writes prevents writes from ever being inserted between a read modify write and its base. Carstamps are instantiated as a tuple with 3 fields that are compared lexicographically. The logical timestamp TS and coordinator ID can be used by a shared register protocol to form an unstable ordering of writes. The read modify write counter, RMWC, can be used by a consensus protocol to stably order read modify writes with respect to their base. And in order to do this correctly, the RMWC of a read modify write must be set to exactly 1 greater than the RMWC of its base. In enforcing this, a read modify writes Carstamp will always immediately follow its base's Carstamp in the lexicographical order, no matter how the TS and ID fields are set by the shared register protocol. For example, 2 writes with Carstamps 310 and 410 would be ordered as shown. RMW1, whose base is W1, will be assigned Carstamp 311. Similarly, RMW2 will be assigned Carstamp 312. RMW3 is properly ordered after its base W2. And because its TS and ID fields are the same as the fields of W2, it is also properly ordered after RMW2, RMW1, and W1 in the Carstamp total order. We use Carstamps to implement a system called Gryff. Gryff achieves both strong synchronization and low read tail latency by using consensus only when necessary for strong synchronization operations. Gryff's read and write protocols are based on a multi-writer variant of the ABD shared register protocol, and its read modify write protocol is based on EPaxos. We modified these two protocols to use Carstamps so that reads, writes, and read modify writes are ordered properly. We also needed to make the commit phase for the read modify write protocol synchronous so that completed read modify writes are visible to subsequent reads. In addition to these modifications for safety, we made modifications to improve read tail latency in the geo-replicated setting. We enable a fast path for read operations so that they can terminate after one round of communication. And we introduce a proxy optimization that allows replicas to coordinate reads for clients in order to increase the likelihood that the fast path is taken. Unfortunately, I don't have time to go into all the details, so if you're interested, please see our paper. Instead, I'll show a simple execution of each operation type just to give a high-level intuition of how Gryff works. Each replica maintains a Carstamp and value for the shared object. Write operations take two phases. In the first phase, a Carstamp is determined to be larger than the current Carstamps at a majority of replicas. And in the second phase, the new Carstamp and value are propagated to a majority. Because the write protocol is based on a shared register protocol, writes are guaranteed to terminate. Read modify write operations are based on EPaxos with an added synchronous commit phase. Thus, when there are no failures, read modify writes take 2 or 3 phases. The stable ordering provided by EPaxos ensures that read modify writes are assigned a Carstamp immediately following their base. So the order of operations based on these Carstamps respects the semantics of read modify writes. Read operations can complete in one phase when they observe the same Carstamp at each replica in a majority. The proxy optimization increases the likelihood that this is the case by making use of the state at a replica co-located with the client during the read protocol. To understand how Gryff performs in practice, we implemented and evaluated it. In particular, our evaluation looks to answer the questions: how do Gryff's read and write protocols affect the read tail latency relative to state-of-the-art protocols? What is the latency of other operation types? How is throughput affected? And what do these results mean for tail-at-scale workloads that are representative of large-scale web applications? In the interest of time, I'll just focus on the first question of read tail latency. So for our experiments, we emulated latencies between real machines in order to create 3 emulated geographic regions. One replica is placed in each region, and clients are co-located with one of the 3 replicas. Our 2 baselines are MultiPaxos and EPaxos. MultiPaxos, or similar leader-based consensus protocols, are used in real systems like etcd, Spanner, Chubby, and CockroachDB. And EPaxos is a research system that improves on MultiPaxos with a leaderless design. To investigate read tail latency, we ran a read-heavy workload representative of real applications against each of these systems. This figure shows the cumulative distribution of read latencies for the experiment. Latency is on the x-axis, and the fraction of reads achieving a given latency is on the y-axis. Further to the left is better, and in particular, further to the left for the top percentiles corresponds to better tail latency. In MultiPaxos, requests are serialized through a leader replica. Clients close to the leader experience relatively low latency. However, clients not co-located with the leader experience additional latency in order to forward their requests to the leader over the wide area network. And this impacts tail latency. In EPaxos, reads can commit in one wide area round trip from any replica to the nearest majority. However, reads cannot complete until they are executed, and EPaxos' execution algorithm blocks until concurrent conflicting operations have been executed. This results in increased read tail latency because some reads must wait for these conflicting operations to arrive from remote replicas and be executed. Gryff's shared register read protocol allows reads to complete in a single wide area round trip from any replica to the nearest majority when all replicas in the majority contain the same state. Furthermore, this allows Gryff to achieve lower read tail latency relative to the baselines. So in conclusion, consensus is a necessary building block for strong synchronization primitives in storage systems, but it is relatively inefficient for simpler read and write operations when compared to shared registers. We introduce consensus after register timestamps, or Carstamps, to safely and efficiently unify consensus and shared registers. We implement Gryff, a linearizable fault-tolerant storage system, using these Carstamps and evaluate its performance relative to the state of the art. Gryff's read latency is about 2 times lower than existing solutions while providing strong synchronization. Thank you for listening, and I'm happy to now take any questions.
This is really cool work. Thank you. Really interesting set of trade-offs there. Can you say a little bit more about what you think are, some real canonical use cases for this kind of register that is a mix of, I get the reads, but a mix of register writes and atomic read modify write?
Yeah, so the question is use cases, and I think, from a high level, many key value store-like systems have this same shared object interface where most operations are gets and puts, but occasionally you'll need a stronger operation like a conditional write or something. And so I think this idea can be applied to many of those types of systems.
Okay. Cool, thank you.
Hi, pretty cool work. So I had a similar question along the lines of the target workloads. In the evaluation figure, you seem to have a pretty high conflict rate. And so I guess I was wondering more, do you have any examples of applications where this sort of thing affects it? Because you're talking about tail latency, so that's usually for high fan-out applications. Does that matter so much for the WAN? Do these conflict rates really show up in practice?
So the question's about what kind of workloads are generally skewed like this. And I think, there's definitely different types of application workloads. Many of them have actually this high conflict ratio where a small fraction of the nodes in the system might be receiving a large percentage of the reads and writes. This is the case in maybe social networking applications where there are popular celebrities or other figures that receive a large portion of the operations in the system. Thank you.
Yeah,
thanks.
All right, let's thank the speaker again.